I had said we were going to start at 11:30 and then I got caught up in conversation. It's 11:32, let's get started. Before we get started, I'm happy to announce that we found the missing laptop. A round of applause. Thank you so much to the leader who brought it through. I think there was some anxiety and panic, but it has been averted, and I did give it through to reception earlier today. We had started with plenary one, which is all about commercial space ventures and sustainable growth. And now we're going to shift the conversation with a technical session, which is all about building resilient space infrastructure and operations for a sustainable future. Here, we're going to examine the role of resilient space infrastructure and operations in promoting sustainability and addressing global challenges. Before we get started with the session, if you joined us after I spoke earlier, I spoke about Slido, slido.com. That is the platform where you can ask your questions to any of the speakers. Leaders, there will be nothing where we raise our hands and do a raise your hand Q&A. Please use slido.com to pose your questions. The speakers will hopefully be able to see it on screen and answer it either during their presentation, if time allows, or at the end during a dedicated question and answer session. The second thing is, today I am the Director of Ceremonies, but I'm also the Director of Time. For those who missed it earlier, I will explain, just like a traffic light for Avin and his team, when he sees the green, 15 minutes are left with the presentation. When he sees the yellow, there's 10 minutes. And when he sees the red, I know in South Africa it means go, 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 you idiot, why did you stop? But today, the red is going to mean stop, not the idiot part. Thank you so much for respecting time, Avin and team. Please join me in welcoming onto the stage the session moderator for the session on building resilient space infrastructure and operations for a sustainable future, the Director of MFT, Avin Mansukram. Over to you.
Thank you, Maud, for the instruction. Always reliable. Like Maud mentioned, I'm a director at MFT. We provide cloud services to the aerospace and satellite sector. Welcome to everyone to visit our booth. We can talk a little bit more about that. I won't say any more. Jump straight into our first speaker. Dr. Chiara Blau is a senior engineer at CSIR with 10 years experience. She's the technical and team lead of the airborne SAR thrust within the group and enjoys system engineering, performance modeling, image and signal analysis. Chiara is also passionate about mentoring and coaching and advocating for youth and women in STEM, as she is the co-founder and co-chair of the CSIR's Women's Forum. Please, let's all welcome Dr. Chiara Blau.
Morning, everyone. Thank you, Avin, for the introduction. So today, my talk is on 2 airborne SAR datasets that we have available for research, development, and innovation purposes, specifically in the SAR remote sensing and Earth observation applications domain. So I hope that I can get to the point where I can show you some of the interesting work that our team has done before I get the red light. Before I start, I just want to give a brief introduction of what is SAR for some of the members in the audience. SAR, or synthetic aperture radar, is a radar sensor, so it's an active sensor, meaning it provides its own illumination of an area or a scene, and that means you can image in day and night. You're not dependent on things like the sun to... okay, thank you. It's going on its own. Let's go back. Okay, thank you. It's a radar sensor. Man, guys, how do I pause? I'll just keep on clicking. It's a radar sensor that's put on a moving platform, like the slide is moving. Support, please. I'll continue talking before my time runs out. So it's a...
I think you might have animation, so he's trying to fix it from the back.
Oh, okay, thank you. they're fixing it. It's a technical problem. But anyway, it's a radar that's put on a moving platform like an aircraft. So yeah, I'm just illustrating with an aircraft, a UAV, or a satellite. And it uses the motion of the platform so that you can get very fine resolution or spatial resolution compared to a normal radar. You can do really interesting things with SAR. You can image large areas with high resolution or with advanced modes. You can use it to detect very small millimeter level changes in a scene, as an example. So you can take changes in things before you can even see it optically or detect it with other sensors. So this brings me to my next slide, that there are many applications that you can use SAR for. Many other countries in the world are already actively using SAR in their operations and in monitoring certain things. I will just highlight a few applications. So what I mentioned with detecting small changes, that makes this very useful and valuable in things like disaster management, because you can use a SAR sensor to detect changes much earlier than you would have if you had people on the ground or using other sensors. So this helps with early warning, helping that people that want to do some analysis of flood monitoring or things like subsidence. It's also very useful in the military environment. There are many applications in this domain. I mean, you can surveil large areas in a short amount of time. You can also use it in the mining industry as an example, where you can detect or monitor activity and safety. I won't go into further details just based on time, but if you would like to talk to me afterwards about further applications, you are more than welcome to. So getting into the details, the team that I work in is the radar team within the Defense and Security Cluster, and we develop SAR sensors. We use these sensors to collect airborne SAR data, and 2 of these data sets we have made available free of charge for research purposes. They were funded by the DSI, so we had 2 measurement campaigns where we collected the data. The one was part of what we refer to as the Gauteng multi-sensor campaign. So the data was mainly captured in the Gauteng region. And the second one was the KwaZulu-Natal campaign, where we captured data mainly in the KwaZulu-Natal area. And the system that we used, I am just showing a few photos of the sensor. It is a sensor developed by the CSIR, funded by DSI. And the main goal is that we use it for technology and SAR application research and development. And it's installed on a light-wing aircraft, so we install it in a Cessna. It's clear to fly on that platform, and then we fly by certain areas and generate the images. Here I'm just showing a high-level overview of the data sets that we collected. The system is designed in such a way that it's very flexible in the way that it is set up, so we can have different antenna configurations, different modes, different frequencies, different polarizations, which makes the data sets very information rich. So for the 2 campaigns, we collected data focusing on a few specific applications. As I mentioned, there are many, but as you can see, for the Gauteng multi-sensor campaign, we were focusing on 6 main applications. So we were collecting data. We identified certain areas and collected data towards disaster management, precision agriculture, mine-related activities, as well as urban area monitoring. We also collected data over some informal settlements and rural areas. And then there are many water-related applications, so we were focusing on water body monitoring as well as wetland mapping. And this whole campaign was a collaboration between many different parties, including government groups, different research councils, people from industry, so it was a big collaborative effort. Then on the KZN campaign, there you can just see the configuration of the system. But here we focused more on infrastructure monitoring, urban area monitoring, as well as disaster management, but specifically related to flooding, and then also on maritime domain awareness application developments. So at the bottom, I'm just showing the flight paths that we flew to collect the data. So this is in the Gauteng region. We covered many different areas, and these are 3 different flight paths focusing on the different applications for the KZN area. So we were actually capturing data as we were flying towards Durban over various areas. There I just listed a few. Captured data in the Durban area, and then on the way back we captured data again. So as I mentioned, these data sets are very information rich. They consist of temporal data sets because we were flying and imaging an area and then flying back, imaging the area again. So this is very useful if you want to detect changes that happened over time in a certain area. It's also multi-frequency, so it included C-band and L-band. And this gives you different advantages and different use cases for different applications. L-band is a lower frequency, so for example, for something like foliage penetration, it can penetrate deeper through the foliage canopy. But compared to C-band, we have higher resolution available. So at C-band, we have up to 25 centimeters compared to L-band, where we have 2 meters. That is also governed by certain ICASA rules that you are allowed to transmit, but also by our own system tech that we have implemented in that system. So also, as I mentioned, the data is freely available. The Gauteng multi-sensor campaign data is already published on DERISA. So anyone that wants to use the data for research purposes are more than welcome to contact me or my team that we can provide that to you. And the CSR is one of the main pillars is collaboration. So we are very eager on collaborating and actively searching for people to collaborate with to help develop remote sensing applications within South Africa and Africa. And we believe that these data sets will help with that. So I'm going to show some, I just want to check the time, where I do not know where, oh, I'm still okay, perfect. Okay, so a few examples of use cases that you can use the data for and what we've used it for. So the one main thing is for disaster management. And as I mentioned, for both of the campaigns we were focusing, one of the focus areas was on disaster management. For the Gauteng multi-sensor campaign 1, the focus was on subsidence. So we imaged various areas where the disaster management center indicated that subsidence or sinkholes are a big issue. So one area that we imaged here, I'm just showing, okay, we're going back, sorry guys. Here I'm just showing a SAR image over the Centurion area. That's basically a dolomite area, so there's many sinkholes. I don't know if you've traveled here with the N1, but they are busy fixing a sinkhole. And we actually imaged that sinkhole as it was busy developing. So our timing was good, but obviously it's not a positive thing. And then we were also imaging many areas in KZN that was heavily affected by the floods in 2022. So that, I mean, those floods, we are all aware that it caused havoc and it caused a lot of loss, life and economic loss. So we imaged these areas, we identified them. I think we imaged 6 different high-risk areas for flooding with the idea that we can create a high-resolution rich data set for baseline mapping that we can then in the future hopefully use if there's a flood again, hopefully there won't be, but that we can use this baseline map to help analyze the disaster, help with recovery processes and so on. The data set consists of L-band, C-band and polarimetric with various baselines over these flooding areas. This is just a SAR image over the Umlazi area in KwaZulu-Natal. So this is a river running through, and that's typically where the flooding is at its worst. Another example, I'm not going to go into much detail on this, but is on urban area monitoring. So here we have 2 images. The one is just from the 2 different campaigns. This is in the I think this was over the Pretoria area. That's the Swartkop Air Force Base. And then this is in Ladysmith. So there's very interesting features like train stations, train tracks, various roads and things that you can use SAR for road condition monitoring, as well as urban area monitoring, monitoring the area of the development of a specific urban area. So next I want to show you some of the things that we've started doing. So we collected data in KwaZulu-Natal towards maritime domain awareness application development. And we had an AIS receiver on board. So for those that don't know about AIS, it's every single ship that's above a certain size needs to have some transponder on board to say who they are, where they're going, what they're doing there. And then you can receive that, see what they're doing, what they are doing there. And what we are trying to do is to develop a dark ship detection mode so that you can detect a ship that's somewhere and not saying who they are, or maybe giving out incorrect information, and try and detect them, geolocate them, and then use AI or classification methods to actually go and classify what type of ship it is. So the image there is a SAR image, it's not an ISAR image, so that's why there's still motion errors. But here we were geolocating a specific ship, we were imaging it, and then we were, with the AIS information, seeing what type of ship that is. I'm not going to go into details, but here you can see this is now a SAR image over the harbor where we were detecting various ships that have been, well, that were docked. The video is showing a video SAR result of one of the ships that we detected in the ocean. Again, this is a SAR image without any motion compensation, but here are some very interesting features where we try and image over different aspect angles, so that's why you're seeing the different colors. That gives us extra information. Another thing that we are doing is to try and use polarimetric information. Again, that's an added advantage that you get from SAR sensors, and specifically the sensors that we have. So here I'm just showing an example of polarimetric decomposed SAR images over a specific area. This is the Google Earth image, and we are trying to highlight man-made things. We're trying to see what can you use and how can you highlight them better. So here I'm just showing two examples of four different decomposition methods, but in these two we can clearly see the man-made targets very nicely highlighted compared to the foliage, like the stuff in the on the golf course. So yeah, there I'm just highlighting them. Okay, that brings me to the end. I think I was on time. Thank you very much. I don't know if there are any questions. Okay. Should I sit there and answer?
Thank you, Dr. Blow, for that expose on SAR. Are there any questions on the Slido? Yes, no, maybe? Guys at the back? No. Maybe there'll be questions at the end. To recap, we covered SAR being an active sensor, covering C and L bands, high resolution, very high resolution, wide applications, and free data sets that we can get from Teresa, or get in touch with Dr. Blow to see how we can further that.
Sorry,
Oh, there are
just see there's
questions.
one
Okay.
question. My email address is on the first slide. I don't know. You
it's
are
not
more than
sure.
welcome to send me an email.
Slides will be delivered? Yes?
It's cblau@csr.co.za.
Yeah, thanks.
Thanks.
I can put it up.
Yeah, you can put it
Yeah?
up, maybe that will help.
Oh, no, it's not connected. Sorry, my mistake.
worries.
Thank you. Our next speaker is Brian Dean from Dragonfly Aerospace. He is the co-founder and CEO, and Dragonfly designs and builds space imaging technology for the purposes of Earth observation and providing insights from space to governments and companies in Africa and around the world. Mr. Brian Dean, thank you.
Thanks. Good morning. Oh, there we go. Okay, I'm going to be talking about a SAR satellite solution for South Africa. So South Africa is ready to do SAR satellites now. We've been building optical imaging satellites for 39 years, designing and building. We've been launching them. We launched the first one 25 years ago. We've launched 4 of them already from South Africa, South African satellites, imaging satellites. And on the CSR side, they have been building radars since the founding of CSR, I believe. Certainly around 75 years ago, they've been working on radar. And they've been doing synthetic aperture radar, SAR, for 29 years. So there's very mature technology now between the satellite capability in primarily the Western Cape and the radar capability here in Pretoria. And, you know, between the team at Dragonfly and the team at CSR, we've been actually fine-tuning a SAR satellite solution for over 5 years now. And you know, I think the time is right now to do a SAR system together in space. So I'm going to give, thank you very much to Chiara. It's a SAR, you're getting a SAR festival here because I'm followed by Villanelle from CSR also on SAR. So there's a little bit of overlap in terms of some of the benefits, but we really wanted to ram it home, so bear with us. So, you know, SAR images, if we compare them to optical images, optical imaging satellites collect light from the sun that is reflected off the surface of the Earth, and then it produces, as a result, I would say, visually better pictures, as you can see on the bottom of the screen. But it only works in the day, and it only works in clear weather conditions. For many people, this is a problem, particularly the cloud, you know, being able to image the land reliably and not have cloud cover is quite a challenge. In contrast, SAR satellites transmit an extremely strong radio wave energy from space that is reflected off the surface and then is collected again by the satellite. This requires much more power than in an optical satellite because of the energy required to cover these distances. But the benefit is that now it can image in the dark, it can image through clouds, it can see through vegetation, through tree cover, as Chiara mentioned, and can even see through camouflage. SAR is very good for detecting change. Again, Chiara kind of explained how that works a bit better and can explain it better than me anyway. But this is, you know, valuable information that is difficult to achieve in other ways. So SAR, it's a real strength of SAR being able to do change detection, particularly changing heights of land in the case of subsidence and the example that Chiara gave. And also tracking the movements of things, so vehicles and things like this, wherever you're seeing the surface having changed, this is something that really stands out in SAR images. SAR payloads also have the ability to change modes during operation. So we can have a SAR satellite that in one moment is giving you a sub-meter, you know, very high resolution image of a scene, and switch of a mode, we can go to low resolution wide swath and cover large areas. So it's quite an adaptable system, which is very useful. So SAR can be done at many different frequencies. Chiara spoke about C-band and L-band. I think in general, basically any frequency works. It's calculating the mathematical properties of the reflection of radio waves. So the bands that we use are primarily driven by regulatory allocations and available technology rather than any specific frequency that's perfect. However, the higher the frequency, the shorter the wavelength, in general, the higher the resolution you can do, and the smaller the payload ends up being in space. And the longer the wavelength, the lower the frequency, in general, the lower the resolution, but the better it can penetrate through interference in between, like cloud, vegetation, whatever. But then the larger it becomes, the more difficult and more complex it is to deploy in space, because you have constraints when we integrate the satellites onto a launch vehicle. So that limits. You end up with big folding structures, which are then complex things to build and test and prove in space. I mean, the caveat here is it's largely actually driven by bandwidth, which is really a regulatory thing. So you can actually do almost most resolutions in most bands. I'll let the scientists or the radar specialists talk about that area in general, but from a practical perspective, from an engineering perspective, from a satellite perspective, we constrain ourselves. We think, what do we want to do with the system? Do we want to be able to you have a long wavelength, what are the implications of it? Or do we want to go with high resolution, and what are the implications of that? And there gives us some sort of indications. The C-band's quite a good one, because you obviously on the long wavelength side, you're looking at the L-band, the S-band, and satellites have flown already with both of these bands. Many satellites flying with X-band, that's obviously geared towards high resolution. And the C-band, they sometimes call it the compromise band, because it's in the middle. So you're getting pretty good resolution, but also the ability to penetrate some of the obstacles between you and the image, the scene that you're interested in. Okay, so probably the most popular band in space is the X-band. This is a majority of commercial players operate. This has the highest resolution, again, primarily because of the bandwidth allocation. You've got up to 1200 megahertz bandwidth available in the ITU regulations. C-band, we have the ability to do typically 300 megahertz, which is limiting you, I think, to around a meter resolution, but there's also the option to apply for an additional bandwidth allocation from ITU, and certainly when you're doing it as a government program, a government national program, you have a bit more freedom in that area, and then you can even bring it down to 50 centimeter resolution with C-band. So it can compete quite nicely with X-band in that way. I won't go into phase coherence for interferometry. I'll let the CSR team talk about that sort of thing. But there's if you look at the application cases, there's many areas where C-band is better than X-band. There's a few where X-band is better than C-band, and there are many where they have similar performance. So in terms of South Africa, what are the benefits that it can bring to us having a C-band SAR system in South Africa? If we think of it firstly as a technology, this is a strategic capability. There's a handful of countries in the world that have access to this technology. We've got it in our hands already. It's an obvious thing to take advantage of that. It also, from a point of view of commercialization of technology, this is something that can make us internationally competitive. Export revenue from SAR satellites sold from built in South Africa and sold from South Africa can be a big driver for export sales in the space industry. But even looking at other industries, I think some of the numbers that were given in the previous panel, we can start talking about the space industry in South Africa now generating in the region of R1 billion per year in export revenue. It's moved. I think we've started to hit critical mass. It's gone from being something that was very niche and a novelty or an interest factor for the economy to something that's actually becoming a meaningful contributor. And that's just on the revenue side. Again, on the previous panel, they spoke about the impact, the extended impact on our advanced manufacturing sector and all other support services to the space industry. So this is high tech stuff, and we've got it in our hands. So I think it's a good idea to take advantage of it. In terms of the applications, again, Chiara presented on the maritime domain awareness side of things. She focused on the potential for dark targets, which are ships that have their AIS receiver off. There's also the fishing side of things. We're losing something in the region of $1 billion per year of fish that's illegally fished out of our waters. This not only is taking food off the table of South Africans, but it also is affecting the livelihood of our fishermen, as well as depleting our fish reserves. We have a big issue with depleting our fish reserves, and this is, to have sustainable fish for the future, you've got to manage it carefully, and this is something we need to start taking seriously. And we need to eradicate illegal fishing. It requires a concerted effort between the Air Force, the Navy, and space assets, but it is possible. And it's something we should take seriously. Mining, we've got lots of, it was a country that's got a long history of mining. We've got fantastic natural resources. Managing those natural resources effectively and for the benefits of all South Africans is an important thing for us. And being able to monitor our mining facilities from space is something where we can cover large areas, and we can do it in a routine way, and we can measure subsidence, which is an important factor. Linear infrastructure, roads, rails, power lines, these are all things that are very good for SAR, firstly because of the ability to cover large areas, and secondly because of the nature of the way that they can measure change detection. So changes to this infrastructure is relatively straightforward to detect with SAR, where it might be more difficult with optical for a range of reasons, including weather, obvious one. Precision agriculture, we had a fantastic talk on yesterday on the precision agriculture that CSR team is doing with Moses. I hope I got it right, Moses. This is something that you do together with optical, but SAR is really good at identifying biomass or characterizing the biomass, which is the volume of plant in a field, and then using that together with the spectral information to understand what's happening in that field and what are the yields that you can expect from it. And then an important one, we're sending troops across Africa to support other countries. We need to give them support, and we can't always have airborne support, but spaceborne support is something we can do across the continent, and I think this is an important factor to take into account as well. Okay, so the satellite. This is a Dragonfly bus with a CSR payload. The satellite is 350 kilograms. This isn't a concept design. This is something we've been maturing over many years, and it's actually a product. The CSR and ourselves are ready to produce this as a product. We've gone through the trade-offs, we've gone through the refinements, we've gone through the R&D phase. We're now at the point where we're moving into the sort of final stages of building a flight system. CSIR is developing the payload up to and qualifying it for flight. They're busy doing this at the moment. And when they're complete with that exercise, we will be ready to build a system together and put it in space. I won't go into all the specs, but we're designing for an 8-year lifetime, which is important for many customers. 1 meter resolution, in Spotlight, 3-meter resolution in strip map. There are many more modes, but this is a simplified diagram. And fantastic data link. We've got the ability to download a lot of data, and we've got propulsion to manage the orbit over time, and we've got good geolocation accuracy in order to make sure that you know what you're imaging. And we've already got a lot of things in place. We've got the ability to build imaging satellites. We build satellite buses. We build satellite components. This is all local in South Africa. We do mission planning and control in South Africa. We have the manufacturing facilities in South Africa. We have environmental testing facilities. And we do the launch and the fueling of our satellite before it goes into space as well. And then getting into the operations side of things, there's the early phase after you launch it, and there's some. I was speaking to somebody yesterday about the stresses involved in launching a satellite, and people were talking about the stress of the launch itself. It's actually probably one of the less stressful bits. The most stressful is when it turns on. The second most stressful is when it releases from the launch vehicle. And the third most stressful thing is the actual launch itself. There, we're happy that they've got that part covered. The rest of it's, we're responsible, and we need to make sure it works well. Obviously, once it's up there, you've got to get it working perfectly. You've got to calibrate the data so that it's scientifically useful and valuable. You've got to sign it off as being ready. And then you've got to take it through routine operations. And we've learned an enormous amount in the last year and a half operating the satellite that we're operating at the moment. I've been practicing this analogy now, so I'll see if it works. But I'm likening it to sort of a Formula One car. And when you launch it, it's pre-season testing. And you've got to get it running perfectly and smoothly as an operating machine. And getting it working in a routine way has been an interesting challenge. And we've learned an enormous amount. And we're now, with the satellite that we've got up, we've imaged. I think Larita said in the last panel, over a petabyte of data we've downloaded from the satellite already. So this is an experience that we apply to the next project, and we've done a lot of automation. We've been working with South African partners, Pink Matter, on the image processing. And in terms of South African capability, we've got pretty much everything that we need between our various partners and suppliers in South Africa to do a project such as this. Okay. Oh, geez, let me see how many more slides I got. I think I'm finished. So what's left? Complete the qualification of the CSR payload. It's already funded. We've got to finish the bus structure. It's the same avionics as the satellite that's flying. But that's an internal thing. For us, this is a recurring product, so it's just a matter of implementing a flight project. We've got to get the allocation of funds at a national level. We've got to kick off the projects, but we can do a 2027 launch. So if there's stakeholders out there who are serious about this, it's ready to go. I think that's it. Thank you very much.
Thanks, Brian. We've got 2 questions from Minky and James, and we'll pick that up at the end if we've got some time. Thank you. Next up, we've got Willie Nell, who is the Chief Radar Engineer at the CSIR, probably responsible for everyone sitting around the table, right? He's worked at there since 1999 passionately, and his fields include target recognition, signature management, and radar systems. Willie wants to build the next satellite for South Africa. Thank you, everyone. Please, let's welcome Willie now.
Missed the first one. There we go. Okay, good morning, everybody. Let's see if everybody's awake after Brian. So let's try this. Good morning, everybody. It's afternoon already. He's awake. Great. So thanks, Brian, for that. I think you covered most of what I wanted to say, so I can sort of just use and talk to my slides in whichever way is required then to sort of fill in the gaps. So I think the important thing is, though, to say that Brian was talking about let's launch the South African satellite. And I have a bigger dream, because I want to see this, and you want to detect the ships properly through those clouds. Even the X-band SARs sometimes in severe stormy weather will not give you the data. Okay, so you have to understand that. Okay, so I think there is opportunity ahead, and that opportunity is not for us to just talk about one, but to talk about many. And that was actually the design criteria that we used when we came up with this, what he calls a Dragonfly C. That's the full satellite. I call it SAR-C, the payload, so the C-band payload. So what we wanted was ideally a payload that's low enough mass, low enough power, with the right resolution, but with polarization. That's the other thing. Most of these current other satellites are not giving you polarization. The commercial ones are mostly all single polarization satellites, driven by cost mostly, okay? And we want the various modes. Many of the constellation satellites make a trade-off. They go for a dish antenna that's an unfurlable dish that's very light, and that way they can build quite a cheap system if you have the technology in country. One thing to say about that tech, we have investigated that. It's not something that we have in South Africa and country. It's not something that will be cheap to develop. And it still gives you a limitation, because now you have an antenna that has a very narrow beam in both directions, and it can't scan that antenna easily. So you can't do wide swath modes with a large dish-based system like that very easily. It requires a lot more effort from that perspective. And then the other thing is, if you want to build a constellation, you want a satellite that's easy to manufacture. So you want a payload that's easy to manufacture. So Brian was not showing all the details. I've got this slide that shows a little bit more of the details. 600 megahertz of bandwidth, so we can, and particularly I'm maybe looking at the military guys here, where maybe the ITU regulation is not always adhered to. And so we can go down to 25 centimeter range resolution with this satellite. We have modes that goes all the way from spotlight modes to sliding spotlight modes to strip map modes to ScanSAR modes. And most of these things has been developed or has been fully simulated and all of that. So there's a lot of work that's gone into it. And we have even some advanced modes that, for example, companies like ISI currently also show, like video SAR, things that we definitely can do. What I'm showing on the picture at the top is the ride share, what it would look like folded up on a ride share mission. And yeah, I'll just answer one of the questions. Many people ask this question: why do you need such a big antenna? Well, you need that antenna because you need to get to 42 roughly dB gain, because you're trying to image stuff that's 700 kilometers away. And the satellite only has so much power. So in that equation, there's like the power that you transmit and then the gain twice. Okay, so the gain there and the gain back. So it helps a lot to have a big antenna, more than it helps to have a big transmitter or a powerful transmitter. And the interesting trade-off is with a phased array like we're building here, well, you get the power together with the big aperture, because every element is actually part of that transmitter. Okay. So some other key elements of this SAR-C payload design, quickly talk you through it. Step one, it's a phased array. So we can start off by imaging a scene, and then very quickly as we're going, change this place that we're imaging to another scene and in another mode, like Brian said. And even if it's flying with its face down, which it can do, image left and right of the satellite. So we can image scenes on both sides. The sort of swath that you're covering about there, or the sort of variability that they're talking about there, that's roughly 45 degrees either side of the satellite. So if the satellite's flying with its face down, you can image anywhere 45 degrees this way or 45 degrees that way. A lot more area that you can cover with a SAR than you can cover with an optical system. Okay. Now it doesn't want to go on. Okay, there we go. The other thing we have in this system that's pretty interesting, it's sort of at the forefront of where spaceborne SAR currently is. It has multiple phase centers in the elevation direction. So you see there's 3 X's there. What it does, we can transmit on, let's say, the red section, and then that gives you a broad illumination area. And then we can receive on all 3, and then with that we can basically form the image over and chase the pulse over the full area. And then that way we get both the combination of high swath and high resolution simultaneously. Okay. The other thing, in the satellite, we have 5 phase centers in the azimuth direction. This gives us all sorts of other interesting things like a long-track interferometry, which allows us to detect moving targets, strip map modes with resolutions that's lower than the standard limit, which is seen as L/2, and wide beam spotlight modes. And what I mean by that is we basically have a mode where we turn the antenna, so instead of it flying with its length axis, flies like, in the opposite direction with its short axis towards the fly direction. Now we can take that beam that can scan so widely, and we can form an image, let's say to the front of the system, and we continue forming that image over this 90-degree area as we fly past it, and we give you a video in high resolution. So we turn what would be a single image sensor into basically a video sensor as well. The other interesting thing is, and this is, Brian has been saying, we've been working on this for me since 2019, this particular design. So this design has come a long way. It's actually sort of, I would say, in generation 3 or revision 3 of the design by now. And the last thing that happened as we responded to an RFP in the UAE was that the client there had a definite requirement that they wanted polarization on the roadmap. They wanted to say, okay, how do you get this satellite to have polarization? And so we came up with a plan to say, well, instead of the way that we were building it previously, we managed to come up with a design that here in the front end you see, this doesn't want to mark it for you, so I'll have to show it like that. You see these sort of double up blocks. Basically what they mean is we have a transmit section inside the last bit of the antenna that transmits on the left side or the right side of every 4 elements. And what we can do now is if we turn those 4 elements into, let's say the left side is H polarization and the right side is V polarization, it really just requires us now to do the redesign of the antenna elements in the front, those patches in the front, to turn them and feed them in the other direction. Then effectively, we can also add polarization. So we are very close to actually having a fully polarized design, and currently my team is working on doing that work on the patch level to improve our patches to be dual pole patches. And in that case, effectively, we will be able to do dual pole or quad pole and systems with this technology. The other thing I wanted to say is it's not just vaporware. So a lot of people, when they talk to us about this, they say, hey, this is all vaporware. It's not vaporware. It's based on hardware that actually exists, and I'm showing real pictures of real hardware that's been used in other systems. Phase array technology at the CSIR has come since 2015, when we had a project called MSR, where we started building transmit arrays for a multistatic radar for the Swiss government, actually. So interestingly enough, they trusted us more than they trusted European partners to come up with what was then seen as a very low-cost phase array design. And so something else I'll say about this is, it is the reason why Hensoldt came to us and said, will you help us build a radar for a ship? Because they realized that these antennas we're building are roughly 10 times cheaper than the way they build them in Europe at present. Okay, thank you. And so lastly then on this slide, I want to show, Brian sort of showed it, but I'll just quickly highlight this fact. The fact that the antenna consists of these multiple things that all look this, sort of copies of each other. We start off with a big array. That big array consists of what we call a wing between hinges so that it can fold up. The wing has all the mechanics and all the electronics behind it to drive this as pretty much as a radar, okay? But the whole wing then again consists of elements, 3 elements in elevation, which I'm showing here zoomed in. And then each one of these things consists again of 3 things, which I'm showing here on the back side of that. So now if you think about this from a production perspective, it means we're building this block. And once we perfect it to build this block, we can build pretty much all the way up to there using the same manufacturing processes for the electronics. And that means that pretty much building this system is an exercise in building electronics. And our country has got an incredible capability in building electronics that comes particularly through the defense, long history in defense. Okay. We might not be great at building cell phones, but we're pretty good at building other types of electronics. Yeah, hopefully one day we'll be at this conference and there'll also be somebody that's building cell phones as well. Because people always ask me that question as well. Do we have the capability to do this in the country? Okay, and then lastly, just one slide about redundancy. The system from the onset, the array, as you could see, consists of many things that are doing the same thing, so there's a lot of redundancy inherent. And in the digital design of the system, there's also this ability, 3 digital systems working together, 2 of them has to be on at any time. So if one of them dies, we switch to the other one and we can carry on going. And as a last sort of interesting thing I'll mention, what we're currently working on is to say we have a redundant data path out of the system here, and we're actually thinking about adding onto that redundant data path the ability to do GPU processing in space. This would be a first for SAR satellites, by the way, and it would give you the ability to say, in the maritime detection mode, you don't have to dump all that data over the wide swath down to Earth. You just send the chips of the actual ships, little video clips of every ship that you detect. Okay, with that, thank you very much.
Thank you, Willie. It seems we've got, we've got 3 more speakers and 36 minutes left.
Take questions.
Can we take one quick question from Minky again? How can we ensure the security of the collected data to ensure national security, enhance national security?
So maybe, I can directly answer that. Brian and I have been talking about this since the start of the satellite. So, and we had this requirement from the start. Data will be encrypted, stored encrypted on the satellite and downlinked encrypted. So certainly somebody else won't be able to just hack our downlink easily. So, yeah. And then it will be downlinked in South Africa. So.
Okay, thank you, Willie. Halfway through, our next speaker is Liago. Liago is a geotechnical engineer and the co-founder of FieldServe. FieldServe provides INSAR and drone-based monitoring solutions to water dams and tailing storage facilities. So a mining application and water application for SAR. Thank you. Let's welcome her. Thank you.
Wow, it's so intimidating speaking in front of so many leaders. Good afternoon, everyone. I'm Liago Sebutuma, and I'm a geotechnical engineer with FieldServe. So today I'm going to be speaking about enhancing safety and sustainability using INSAR-based monitoring solutions for tailings storage facilities and water dams. In 2019, in Brazil, a huge catastrophe happened. The Brumadinho Dam collapsed, resulting in the loss of 270 lives, as well as significant environmental damage. This highlighted the need for stricter regulations as well as safer practices in tailings management. So in 2020, the United Nations Environmental Programme, as well as the International Council of Mining and Metals, created the GISCM, which is a global industry standard for tailings dam monitoring. The GISCM provides comprehensive guidelines on how to safely manage tailings dam in order to save lives as well as to preserve the environment. One key aspect of the GISCM is the need to use INSAR, drones, as well as real-time data systems. Yet again, in 2022, bringing it closer to home, we had another dam collapse of the Jagersfontein in South Africa. This was after the adoption of the GISCM in 2020. But still, dam failures continue to happen. And ladies and gentlemen, this is because in South Africa, more than half of our tailings dams, and dams in general, are not being properly monitored. And those that are being monitored, some are not being monitored, those that are being monitored using traditional methods. And these traditional methods have their shortcomings. The current challenges of monitoring tailings dam using the traditional methods include the inaccessibility of the dams. Many dams are in remote locations. Usually dams are in mountainous regions or in areas where there's dense forestation. so it makes it difficult to physically access these dams. Some dams, because of their complex structures, cannot be accessed without specialized equipment. Secondly, when monitoring dams, we need to cover large areas because dams are vast and many of them cover several kilometers, including the upstream and the downstream side of the dams. This means that if you are using ground-based sensors, these sensors are not going to be able to cover the entire wall. So the point-based nature of a ground sensor will mean that the information that you receive is localized, which means this information that applies to this ground sensor may not apply all over the dam. Lastly, we need real-time data. The traditional methods offer data reports at a delayed rate. We need technologies that are going to give us data when we need it to prevent disasters as soon as we realize there is a problem. So how do we use INSA in dam monitoring? Firstly, the most important feature of INSA is the fact that it allows us to have early warning signals. We use INSA in dam monitoring for slope stability assessments, tailing storage facility beach length monitoring, as well as moisture mapping. The picture you see here is a picture of an eco-sounder. An eco-sounder is mostly used when we measure water levels using the eco-sounder so that our water level, we make sure that the water level of the dam is not overfilling and that we do not have overtopping of the dam. We also use the eco-sounder when we are trying to assess the sedimentation distribution. We need to ensure that the sedimentation in the dam is distributed evenly, or at least according to the design, and not have sedimentation settling only in one area of the dam. And lastly, we use these drones for close-up views. Whenever we realize that there is a high-risk area, we can send through a dam so that it can focus on the high-risk area and take the imagery that we require. So how do we use the two technologies together for better safety enhancement? So when we use the INSA, we can have continuous monitoring of the tailings dam using INSA. So the satellite will go throughout, will give us readings for every 6 to 12 days, and then we can keep a record of our data. From there, should we realize that there is a reading that is outside of our threshold, we need a quick response in order to investigate what is going on. This is when we send through our drone. The drone then goes and focuses on the high-risk area and then gives us the data that we need to diagnose the situation. So, ladies and gentlemen, this will give us it will save us a lot of money because we are able to limit the number of times we have site inspections because we just have the continuous tailings monitoring, and should there be a need, we will strategically deploy a drone. In conclusion, we can say that the integration of INSA into our dam monitoring represents the advancement of safety in our dam monitoring culture. But an important thing to remember is that INSA is a complementary tool at this stage. What we mean by that is that when we use INSA, it is very important that we connect INSA and we use a complementary technology such as either drones or ground sensors so that we can have better benefit of INSA. Lastly, it is important that we realize that when we are monitoring, it's not just about using the latest technology, but it's also about ensuring that the first thing is safety of communities that are around the dams, as well as safety of the environment. Thank you.
Thank you, Leacho. Thank you. Thank you. There are quite a few questions that have come up on the Slido. We have been able to claw back quite some time, so thank you very much. Can we reserve that to the end? Let's finish our two more speakers, two additional speakers. Zambini from the CSIR atmospheric researcher with more than 5 years experience, and she's currently contributing her experience and her expertise to the optronic sensor systems impact area under the Defense and Security Cluster. Everyone, thank you.
Good day, everyone. Standing in front of you is Zimbini Fani Somnyaka. As the speaker has said, I'm from CSIR. So today I'll be talking to you about the role of vicarious calibration and validation target sites in enhancing satellite Earth observation sensor accuracy. All right. So as we have heard even since yesterday, the importance of satellite Earth observations in our communities and also in our world as a whole. We know that they help us to monitor environmental changes, disaster management, such as flooding, fires, droughts, and also they provide us with knowledge through providing the data, to monitor agriculture and also give us information to know what to crop, when, and how. And also recently, if we understand that our world is currently migrating to the use of solars, so even the satellites have migrated to have IR cameras so that they can be able to detect solar faults. So basically, this is how satellite Earth observations are important to our world. However, when a satellite sensor is deployed into space, it encounters a lot of challenges. So as it is deployed, some of the optical effects that it encounters include different gases, absorptions, which are some of the optical properties that take place. So all of those, they can have an impact on the data that we get. And also, as the sensor is being designed, it is designed to operate on certain wavelengths. So basically it is wavelength dependent, meaning on some areas it can be able to penetrate through the lower grounds, whereas on some areas it can. Then one thing that is also helpful is that on areas where it can't or it can penetrate through the lower grounds, there are also ground sensors that have to be put in place so that the satellite can be able to overpass and also do something called vicarious calibration, which I'm going to speak about on the next slide. Also, in that preparation, we also use things like, or we require, atmospheric modeling so that we can see how is the sensor going to operate or sort of estimate the type of data that we're going to get when the sensor is up in orbit. So some of the models that they normally use are MoTrain, for example, where you can model your atmosphere, try to simulate the presence of atmospheric transmission and see what type of data you can get. So what is vicarious calibration, basically? So vicarious calibration is a technique that is used to calibrate remote sensing instruments when they are in orbit. So it is currently a challenging issue. We do deploy sensors into space, but we don't know if the data that we are getting is really accurate. So it does that by also comparing the sensor measurements with known reference data. So if you can remember from my previous slide where I spoke about ground sensors that are being deployed on certain areas around the ground, that is where now the satellite will target such areas where there are ground instruments to overpass so that that data can be able to be compared to the data that is obtained by the satellite, and that's how the vicarious calibration is being done. And then validation now is the process of independently means the quality of the data products derived from the system is to process that data and also ensure that it is the data that it was expected when the sensor was being deployed into space. So these vicarious target sites, some of them are natural, some of them are artificial. So the natural ones, they can be your big lakes, your certain dry areas or deserts all around the country, but I will talk more on that on the next slide. But there's a certain requirement that each and every calibration site must have. So they should be very specially large areas, and they should be flat, and they shouldn't be uneven. They should be homogeneous so that when the sensor is overpassing, can be able to characterize the area. And the most importantly, they should be highly reflective. So your surface, you must make sure that it is highly reflective so that it can be detected by the sensor as it is moving in orbit. So these are some of the examples of the natural calval sites that are being currently used by certain satellites around the world. So we've got the Eroges Dry Lake in US. That's a calval target site. It is a very dry lake bed area with high reflecting surface. It is currently being used by certain satellites. And also we've got another one in USA, which is a railroad valley playa. So that one, it was mostly used by Landsat and MODIS to calibrate their data. And another one is in Namibia, which is a large hyper-arid desert area that they use because it has got minimal vegetation, and it has also shown stable atmospheric conditions as they've been doing the measurements in all the years they've been deployed their sensors. So these are just some of the examples, but there are quite a few of them out there, and there's still a need for more, especially in our country, South Africa. So what methods does the vicarious calibration use? The most methods that are mostly used are two of them is absolute calibration. So the absolute calibration is whereby the sensor will overpass the area with ground instruments simultaneously, and then after that the data will be compared to the sensor and see if there are any errors that need to be corrected, or verify if the sensor is still operating the same way as it was expected to operate before. However, the advantages for this one is that it provides the direct and precise comparison with known targets, and also it is effective for correcting systematic errors in the sensor data. However, there are also challenges because it requires access to stable and well-characterized ground targets, meaning you should have more information about these known targets that you want to overpass on. You need to have as much more information as you can. Then also it can involve significant logistical and operation efforts, meaning you have to put people into place on the same time, make sure that the people are there at the same time as the satellite is going to overpass. So that could be a challenge sometimes. Also sometimes the weather can be a challenge and makes you to rearrange things as time goes on. So we also have relative calibration. So it also uses relative calibration. Here, this is where the sensor data is being compared to other sensor data again. And then different methods are used again, which is reference comparison, which is where I just mentioned you compare the satellite data with the other satellite sensor data. Also temporal analysis, which is now to analyze the variations in the data over time to identify any correct drifts or anomalies on the data so that we can have you can be sure that your data is accurate. However, there's also cross-calibration. So this one is when they use the data from different satellite sensors, which is similar sensors and different satellites to adjust and validate each other now. So it's called cross-calibration. The advantages for this type or this method of vicarious calibration is that it's useful for maintaining consistency between different sensors over time, and also it can be applied when absolute reference targets are not available. However, the challenges that you may encounter is that it may not correctly correct your absolute errors, but ensures relative consistency, and also it depends on the availability and accuracy of reference measurements. So CSIR back in 2014 did embark on a journey to try and find or build its own artificial target site. It's down there in Parafontein. So it was the campaign, it was a collaboration between DSI, CSR Overseas, and SANSA. And the campaign was a success, and few satellites were invited to do the overpass. One of the satellites that managed to overpass that time was the Pleiades satellite. So if you can see down there, this is the satellite sensor images, Pleiades, that was overpassing on that day. So this is how the Calval site, it's a 100 by 100 meter site, concrete area that was developed specifically to play a part on calibrating onboard sensors. So I also want to highlight that due to funding, again, there were more challenges. We couldn't really get the data that we want, because the aim was to collect as much data as we can. However, this project is currently operating as we speak. We are on a journey to revisit the area, and also now make sure that we have got instruments that are there all the time collecting data and keep the data so that it can be used. We will also invite researchers, universities to be able to test the data, and also invite other satellites who are planning to do deployment so that they can use the area to do their, to calibrate their sensors. So it is an ongoing project as we speak. So in conclusion, we've noticed that it is important to have accurate data so that we can be sure that whatever that we want to look, or whatever disaster that we want to observe, to ensure that the data that we're having, it is really accurate. So vicarious calibration plays a vital role in refining the accuracy of satellite Earth observation centers by leveraging ground-based and airborne measurements, and also employing both absolute and relative calibration methods, as I've mentioned before. And also, we can significantly reduce uncertainties and improve the reliability of satellite data through the vicarious calibrations. It is also essential to build resilience and sustainability in our space infrastructure, because there's an increase in the deployment of satellites. We can observe daily there are a lot of satellites that are being deployed in this place, it is necessary to have these calibration sites on board so that our satellites can have really an accurate data. So having high quality data from satellite sensors, it underpins our ability to monitor, understand, and respond to dynamic conditions of our planet. So in closing, it is very important that we investigate in vicarious calibration initiatives to ensure that we continue to enhance the accuracy of our satellite observation. And also, it is a demand for Earth observation data, because it is growing massively, as I've said before, about the constant deployment of satellites into space. So in my closing remarks, I would like to say that I would like to encourage the development of calibration sites capability on our space communities to drive forward the development of resilient and sustainable space operations. Through continued collaboration and innovation, we will ensure that our satellite Earth observation systems are accurate, reliable, and integral to our understanding of the world. That's it on my presentation. Thank you.
Thank you very much. Thank you, Zimbini. We have quite a few more questions that have come through. We'll hold that to the end. Now we get to the last one. Dean, my favorite part of the talk around cloud and how we can contribute to the industry. Dean is an accomplished geospatial professional with more than 20 years of experience in the industry. He has a master's degree from UCT. Dean works with the aerospace and satellite team at AWS, where we are tied to as well. And he supports customers primarily in the downstream segment of the space value chain. His presentation, titled AWS for Geospatial, will delve into the various AWS services and solutions that are transforming the geospatial industry. Thank you, Dean. Welcome.
Good afternoon, everyone. Thanks, Avin. Okay, final session, or final presentation of this session, so I'll try to respect the time. So the title of my presentation is AWS for geospatial. So in brief, what I intend to cover today is really the intersection between the geospatial world and the AWS cloud. And what I'd like to do is sort of leave you with 3 takeaways from today. Number 1, geospatial data is big and it's getting bigger. Number 2, good news is there's help at hand because a lot of the hyperscalers, cloud providers today, including AWS, are increasingly used to handle big data, particularly geospatial data. And thirdly, by aggregating big geospatial data on the cloud, we're starting to lead to new ways to find, discover, to query, to analyze, and extract value from your big data investments. So let me start by talking about big data in the context of satellite imagery. So as we know today, there's a lot of satellites up there. The images you see here, the first one on the left, is essentially satellites in geostationary orbit, MEO orbit, but if you start to drill down further into LEO, you see a tremendous number of Earth observation satellites. And it's these satellites that are contributing significantly to what essentially is a geospatial data tsunami. So between 1950 and 2008, I believe there are around 180 Earth observation satellites orbiting the Earth. Today, there are more than 1,000. And of course, with each new deployment, we're getting more sophisticated sensors, and those sensors are able to capture data at greater coverage, greater frequency, greater bit depth, and of course, greater resolution. So we're at a point today where, on a daily basis, we're imaging or capturing data from Earth observation satellites of order of magnitude of more than 100 terabytes a day, which translates to around 36 petabytes per year. And of course, that number is continuing to increase. So geospatial data is getting big, is big, and it's getting bigger. So from a satellite point of view, satellite data point of view, how do we get that into a cloud service or into the cloud like AWS? So one of the interesting ways in which we can achieve that is through AWS Ground Station. So what is AWS Ground Station? It's a fully managed service that lets you control your satellite communications, to process the data, and scale your operations without having to build out that infrastructure and manage your your ground station infrastructure. And with AWS Ground Station, you can downlink data from your satellites to one of 12 ground station antenna locations, and then land that data directly into an AWS region of choice. And obviously this leads to much less latency than more traditional means. So who's using ground station? Well, we've got companies like Capella Space, and they're able to track daily changes on the Earth using their constellation of satellites, which are paired with AWS Ground Station. And from that, they provide low latency, fully automated pipeline to get their satellite data to their customers so that they can make better informed decisions in a more timely manner, particularly in a time of crisis. And moving forward, Capella Space anticipates that they will generate upwards of 500 petabytes of data. Okay, so the question is, once you connect to the antenna, where does that data generally end up? Well, at AWS, we have a service called S3. For those of you not familiar with it, it's an object storage service. S3 stands for Simple Storage Service. It's highly scalable, it's highly available, highly durable, and importantly, it's inherently secure. And this allows users to store and retrieve any amount of data from anywhere on the web. So we talk about 500 petabytes of data for Capella Space. That might appear to be an enormous number, but for AWS S3, or for Amazon S3, it's a proverbial drop in the S3 bucket. So just to give you some sort of idea about the volumes of data and objects that are stored in S3, according to recent statistics, S3 is holding more than 280 trillion objects. It averages over 100 million requests per second, and through a service called S3 replication, it is moving around more than 100 petabytes of data on a weekly basis. So yes, geospatial data is big. AWS can handle it, and it can do so without any of the extensive planning and upfront costs that are required for customers to expand and add data centers. And so moving forward, we're seeing a lot more increasing use of S3, particularly to store and handle geospatial data sets. Many of these data sets are intended for public consumption. So at this point, I just want to highlight the Open Data Registry at AWS, in case you're not aware of it. And so through the Open Data, the AWS Open Data Sponsorship Program, organizations can partner with AWS and to host their high-value public data sets at no cost. And obviously the upside of that is it allows for democratization of the data and encourages communities of interest to organize around these shared data sets. So what kinds of data are we currently storing through the Open Data Registry, which you can access today? OpenStreetMaps, Sentinel-2, we've also got USGS Landsat imagery, USGS 3D elevation program, LiDAR data sets, OpenAQ air quality data sets, just to name a few. So there's currently around 160 petabytes of data that we are hosting on behalf of those that want to share their high-value public data sets. But S3 is not the only place in which we can store geospatial data. Different use cases and access patterns require different data stores and analytic services. So for example, if your data is stored in Amazon S3 bucket, in some cases it might make sense to use a service called Amazon Athena to perform SQL queries against that data. And moreover, with Amazon Athena, there are a set of geospatial functions available to make geospatial-aware SQL queries. And if you're in the business of doing online analytical processing, we have a service called Redshift, which is a fully managed data warehouse service. And through Amazon Redshift, similar to Amazon Athena, you'll also be able to have a set of geospatial functions that you can use to query the data for geospatial-aware context. And then for online transaction processing, that require traditional relational databases. Many of our customers are using a service called Relational Database Service, which can host common relational databases such as SQL Server, Oracle, MySQL, and of course the popular open source Postgres, to which you can add on top of that a Postgres extension. And the Postgres extension gives you a comprehensive set of geospatial functions that is widely interoperable with geospatial software across the industry. And then finally, for real-time search and analytics and data visualization use cases, we have a service called Open Search Service, which supports geographic data types, geographic functions, as well as map-based visualizations via Kibana dashboards. Okay, so we've got the data in the cloud. Now what? How do we perform some analytics? Okay, so typically, many customers are using commercial off-the-shelf GIS or open source, so that could be an ArcGIS, GRASS, or perhaps a QGIS, and they want to be able to access that data through an S3 bucket that that is stored somewhere on the cloud. Or it could be on a GIS server on an EC2 instance, which is our virtual server running on AWS, or it could be stored in an RDS database. Common questions we are asked is, what about latency and what about the transfer cost, the movement of that data out of the cloud, so-called egress costs? Well, the solution to that really is to leave the data in place and to bring the compute resources needed to the data and avoid copying the data around. I feel like I'm being sent off the football field here. So there are a few patterns that one can adopt to achieving this. First of all, there's a so-called VDI, Virtual Desktop Infrastructure, and we have two solutions for that. Something called Amazon Workspaces and Amazon AppStream. I'm not going to go into the details of the key differentiators there, but essentially, with these services, users are just streaming the pixels representing the screen over the internet to the local devices. Another popular approach, and I've got a couple of slides left, is to use data science notebooks like Jupyter notebooks, which is quite a popular option. So here what we can do is spin up a Jupyter notebook server. We can then use a web browser for our consumer to be able to access that server. And the underlying, at least the server contains the underlying compute resources to access the actual data. Jupyter Notebooks is also becoming very popular when paired with Python programming language and a number of geospatial libraries. If you're familiar with these, ArcPy, Shapely, and GeoPandas. And if the notebook server does not have enough compute power to handle the desired geospatial analysis, another advantage of cloud computing, of course, is the ability to spin up a cluster of services directly from Jupyter Notebooks. I just want to briefly talk about machine learning. So in traditional analytics and high-performance compute use cases, we have customers interested in applying, in addition to that rather, we have customers interested in applying machine learning to geospatial data. So in 2022, we announced a service called Geospatial ML with Amazon SageMaker, which is a new capability that allows you to build, to train, to deploy machine learning models using geospatial data. And through the service, you can gain access to a rich catalog of data sources, or you can bring your own data. From there, users can then use pre-trained models or train their own model before deploying it into a managed endpoint. Moreover, geospatial machine learning for geospatial also allows users to visualize the results of the models on an intuitive map interface as depicted in the top right image. Second last slide, promise. I just want to talk about another service that we offer called location services. Location services allow developers to add location functionality to their applications. The kind of services that we have include maps, to embed maps into your user interfaces. We have places to add location search to your applications. We have trackers, so you can track assets like delivery vehicles. Wouldn't surprise you working for Amazon that this is a service that we offer. And then we have route optimization tools as well. So, just to conclude, once again, geospatial data is getting a lot bigger. Cloud service providers are more and more equipped to handle geospatial workloads. And so hopefully today I've kind of highlighted at a very high level some of the services that we offer in order to handle, to manage, to process, analyze, and extract value from your geospatial data sets. And with that, I want to thank you for your time and attention. Thank you.
Thanks, Steve.
Sure.
There are quite a few questions that have come through on Slido, and unfortunately we are 5 minutes over for lunch. Thank you to our speakers. Thank you to the guys for listening, for your questions. If you are able to hang around for a few minutes, we can take some of the questions, but the lunch will still continue, so you're welcome to join that as well. Thank you, guys.